All right. So let's get back to differential equations. Just as a review of the last time, we introduced differential equations and a numerical solution to differential equations. Don't be afraid if you don't like differential equations from your math class. Don't be afraid of this one because you will not need to basically solve them analytically. The whole point is that there is only a small class of problems have actually analytical solution. A lot of times we will derive a differential equation and it will not necessarily be pretty enough to be able to solve it analytically. And in those cases we often have to go to solutions, numerical solutions. This is even more the case. So ordinary differential equations are dealing with functions of one variable. If you have functions of multiple variables, like f of x, y, and so forth, that's where you involve partial derivatives in the equation. You involve partial derivatives of your function. Then you have partial differential equations, and those get even nastier. Nastier in the sense that it's hard to find solutions. So a lot of engineering problems of interest, and you will get to transport phenomena next year probably. Is anybody taking transport phenomena now? There's one person. So you will get to transport phenomena, and for instance, one of the most common equations that is employed is Navier-Stokes equation, which basically defines how fluid flows. Okay? We, of course, in petroleum engineering, we need to know how fluid flows because without fluid flowing, there's no business. So essentially, that equation is as nonlinear as they get, in the sense that the solution can be really ugly. There is no mathematical proof that there is a solution, or not a unique one. We often have, and if you have poured milk into your coffee this morning, you have seen some turbulence, right? You often have turbulence even on a very relatively small or benign scale. And that how is that milk going to mix in with your coffee business is not something we can easily predict. Not exactly, not deterministically. So in such cases, you simply have to go to numerical solutions, and this lesson is a very introductory lesson on ordinary differential equations, but basically shows you a way how problems like this are solved numerically. Again, for something like Navier-Stokes equation, that's a partial differential equation, so it's much more involved than what we're showing here in class, but that's something to keep in mind. That's something that you want to solve because it's of practical engineering interest. All right? So let's go back to our very simple problem. We had a problem where we had dy dx is some function of both x and y. And we pose an initial value problem, meaning that we have at one point, at one endpoint, we actually have a boundary condition or initial value. So basically for x is equal to 0, I have y of 0 given. After that point, I will keep iterating and find other solutions. So for every, let's go next point, so I will basically discretize my interval of interest. So I will start from that point where I have the solution. And then for every next one, I'm going to say, my next value of y is my old value plus some slope times h. H is the difference between x values corresponding to yi and yi plus 1. We call them xi and xi plus 1. Okay? So this is actually, we saw last time, it's actually, I can get this from Taylor series, or I can get it visually. Essentially what I'm doing at point xi, okay, this is my value yi, so this point here is xi, yi, oops. And then I'm just going to take the slope, which is the first order derivative, and I'm going to extend that slope for this distance or step size h, and this is going to be my prediction for yi plus 1. I can see that here I'm pretty much far away from the actual solution. Okay? So how can I improve this? How do I improve on that? The only basically, once I have a way to find the slope, the only way to go about reducing this error is to take a smaller step. Okay? So essentially by making the step, this step smaller, so basically if my h is smaller, I will be here and I will be much closer to the actual solution. Okay? So this is Euler's method, and essentially since my dy dx is f of xi yi, it's actually really simple to evaluate this slope phi for Euler's method. So the simplest way is just to take f of xi yi at every stop, and I keep iterating. Now, this is not the type of iteration where I keep iterating until my error is small. This is actually I'm calculating value of y at every different point x. Okay? So as I'm iterating, I just keep actually computing new solutions. Okay? So it's as accurate as it is, essentially. So I don't iterate until my error is small in this particular case. Okay, so this is one example where I might have a function. So here at this point, 0, this is my slope. So if my step size is 0.5, then then the method is gonna take me to here, and then here, and so forth. Okay, so here at this point, I evaluate the slope. This is the slope. Therefore, my next point will be here. I just take it for this step 0.5, and I keep going like that. So here I'm off quite a bit, but if I take a smaller step size, I'm actually going to be somewhere here in between. Okay. So this is the recap of the Euler's method, and if I actually look at it, I can see the Euler's method as truncated. So if I take all of this away, I can see the Euler's method as a truncated Taylor series. So Taylor series motivates a lot of things. So this proportion here is essentially my Euler's method. So then the error that I'm making at every point is basically this, the stuff that I chopped off. Okay? So that's the truncation error at every step. But I also have to remember that at every step, I'm using something that I have previously computed that has error in it as well. Therefore, I'm piling up quite a bit of error. So here I would hope that my error would be, this is called of second order, that it depends on h squared. It depends on h squared at every step, but since I'm piling up error from before, I essentially get the order of h, so-called error. So ultimately, the piled up error is of the first order. Okay? So this is the promise that as I'm taking smaller step, I improve. So you have gotten through your exercise. How many of you have completed the exercise last time? Some. Let's just take a couple of minutes. So please go back to your code and try to finish it up. And then we'll discuss it. So we have computed this part by hand last time, no need to do that again. But I want you to actually finish up this program quickly. Yeah, that's right. So, same. Myself a separate function.
Yeah, I'll show you.
Same. So try it. Yeah, let's use it. This should work. No need to put here. Because we don't. We have analytical solution, so we can do that. But just plot it against the analytical solution. That's essentially it. So did you define yourself the first point?
Oh, I didn't. Well, I mean, you input
Why one? Yes. But so here it has to be the efficient. So it's why
okay.
the only problem here.
Can you write like that?
Yeah, the thing is that if you have to refer to y's with the same number than the same rate as you do at the system. So then it's the previous one.
What was it afterwards? Should I be able to run it right now?
You save, but you have to run
Yeah,
the
yeah.
beginning So what do I have to actually have you do this one? That's actually a simple formula. Do you write that? It's just not one that we'll figure out how to do it. Missing, right? This is my internal thing with what and there should be spacing. So your x's, they start with x1 and then it's your spacing. So how do I define that? So those are my x's. And then my first one is my so I'm just going to say Is it okay? So it has to, so the logic here is like, that's one way to do it. So now you have those, now you're missing the side. So this is a very simple function, it's a polynomial that depends on the x. And you want to evaluate it for the x. So you have to either define a function outside of this function, or you define a formula. Huh? And this decision. Equals. This is yes. Yes. Hmm?
Oh,
And the other one, keep it because that's your analytical solution, or call this analytical or something, because you want to work against that.
And
I don't know. So work on I would go from I1 to number of elements. I mean, this is your analytical solution. Like this, how are you going to get the other one? Because you now want to refer to I as something that is numbering things, but at the same time you're referring to I as an actual side. I would just say. How about saying no, I would call this
I was doing it because I thought I would use it.
the last one. Yes. And plug. You gotta plug. How are we doing?
That shouldn't change your answer. We have one.
Analytical solution.
Like we could have gotten the same answer.
The same X is compute analytical solution. Or you can compute it all. Yeah, mixed modes, yeah. So it's pretty. I agree.
Yeah.
Check out the
Okay.
Because then you're gonna have 1, 2, 3, 4. X1 and
And so I can I'll change those two now y. But I want to do this so that it goes from
so that every space
So I wanna-
page
I want to use this formula.
this loop.
So I was going to do it, but I use this color for the group.
Using
On the
Yes, I think so. So constantly say X, Y, X1, because this Y, this Y1 is
Yeah. That's
Alright, so most of you have at least gotten a chance to try it out. So I actually named things slightly differently when I was solving. But basic iteration function takes x1, xn or x maximum h and a y1. And first I get myself, this is discretizing x's, right? So I'm getting a vector of x's, and every h I have one value of x. So I can get that by this. If you want xn, I can work with xn. Okay. And then I'm just gonna, I can allocate memory for y values. We know we don't need to in MATLAB, it's gonna survive without it, but it's a good idea to do that. And you set your first value to y1, that's your initial point. This is initial value problem. And then for the rest of the values of x, I'm gonna get y corresponding y value. Okay, for every x of I, there's a corresponding value y of I. as my previous value, y of I minus 1, times value of f, and I actually have a separate function f in this file times h, and that's pretty much the end of it. That's the end of iteration. At the end of this iteration, I have both all of the y values and x values, and I'm returning them. So let's see my function f. This is my function f x y. I like defining functions old style. You could have done an inline function, that's just fine. And I also have an analytical value of x programmed as well. So if I compare the two, this is how I would initialize it. I would start with my initial values and h of 0.1, and then I just execute it, and I have these vectors, and then I can plot them. And this is going to be red diamonds, and I can also plot the analytical value. So I have a much finer discretization for analytical value, so we get like a very nice smooth, and I can evaluate it and plot. So let's actually execute this, save. I was changing it, I hope I didn't break anything. Okay. So essentially, this is my Euler's, and this is analytical. Let's now execute. So the promise is that if I reduce my step, I'm going to get better. Let's try. So let's see. So let's kind of recall how this looked like and run it. Okay. So basically, this is what I added in between. So if I now go even better, I'm going to get actually rather close to the analytical solution. Okay? Questions? Did everybody get somewhere on the line here? Close? So the actual iteration is actually relatively simple. All you do, you have a rule of how do you get to the next value from the previous one. So you just type that in. And when you type that in, then you start filling what's missing. Okay, what are my xi's? What are my endpoints? What is my function f? So then once you fill that in, you're actually done with the program. Okay? Questions? All right. Let's learn some more methods. This is actually the simplest, the crudest one, the simplest one, and therefore it's not the most accurate one around. Okay? So now we will actually modify it. There is Heun's method. I'm reading it in a German way. Heun. I don't know what would an English speaker do with this. H-E-U-N. Heun, maybe? I don't know. Okay, I'm gonna I'm gonna stick with German since Heun's method or modified Euler. Euler was German as well, so I'm just gonna stick with it. So in this particular case, I'm looking to improve. So what we did in Euler's method, we said, slope here, f of xi, yi. I'm just going to keep going for my step size h, and this is going to be where this Euler's method takes me. Now, Heun said, well, maybe I can improve that a little bit. If I actually now take wherever it is that I got, this is my new proposed value of y, okay, yi plus 1. Well, at that proposed value, I have a slope as well. So if I average the two slopes and take that as a slope to take, well, that will maybe improve my standing. So basically, if I average this slope with this slope, I'm going to get something in between. So basically, because I'm in between, I'm going to be more accurate. Okay? So first, you evaluate this midpoint, so to speak, the so-called prediction. And then using prediction yi plus 1, 0. So this is your prediction based on Euler's method. Using that prediction, you find that slope too and average the two slopes. Okay? So this is what it does visually. So essentially, if I was taking this slope, so this is the slope that is actual slope. This would be my prediction based on Euler's method.
Which is your actual slope, the orange one?
This red one here. That's slope. Okay? So this slope here, it's not actually the best accuracy of drawing these slopes, but it was hand drawn. Okay? So then between this slope, this would be the slope actually at this prediction value, this one here. So between the two slopes, if I average them, this yellow would be my resulting slope. Okay? So this is the one as per Euler. That method took me to this point. At this point, this is the slope, this black. Okay? And the parallel is taken here as red. So essentially, if I average the two slopes, I'm halfway in between this line and that line, and this is where the method takes me. Okay? So when I put that in formulas, I get this prediction for y value, which I call yi plus 1, 0. Okay, at every point I have a prediction first. I use that prediction to find my new slope. So this is my f of xi plus 1, and this is my prediction value of y. So I take that slope and this initial slope and average them, and that's the slope that I'm going with. So I have really just one more computation step in that Euler's method. Yes?
So does this method run the risk of failing around its schema because we're averaging and we divide by something really close to zero?
Yeah.
Will it fix itself or will it try to?
That's good. No, it's just gonna get stuck at that point.
It'll get back.
Yeah. But I keep adding things, so I'm gonna just add something that is relatively zero. So it's close to 0, hopefully not just precisely 0, and the next step I might actually fix that. Yeah? So this is the average of the two that I'm going to take, and this is my so-called corrector equation. So there's predictor equation and corrector equation. And I will converge supposedly faster. So how about you for the, let me see. And then we just go to fourth orders. Yes. So do you choose to implement this method right now, or do you want to introduce one more, like open-ended? You have a choice. Do you want me to introduce one more before we go and program?
Yeah.
Okay, all right. So then at the end we'll actually get to exercise them all. All right, so this is actually a relatively easy one-line correction to your Euler's method. To actually, we just have to introduce this intermediate value, right, and compute one more slope and average the two. So it's not a lot of work to actually modify the code that you have for Euler method. Now I could actually choose, since at least visually in that example that I've shown, which was here, this kind of seemed to really improve the matters a lot. I could technically choose, and sometimes people do, to actually iterate on this correction. So I can actually keep correcting, and that could actually fix the problem around zeros. So actually keep correcting around this value here. So I can actually repeat this process until I get error down to between the two consecutive values of y down to whatever I'd like it to be, 0.01 or some sort of epsilon that we have. And that's so-called iterating on corrector equation. Yes?
Can you explain what you mean by iterating this process?
So I'm just going to actually have a separate, instead of just doing this once, okay? So I find this prediction, I find this slope, and I find the new value of yi plus 1, and I say I'm done. Instead of saying I'm done, okay, I'm actually going to take this as an old value and take last two values of y that I have here and keep computing this value. Okay, does that make sense? So I'm just going to keep looping, computing new value of yi plus 1 using two older values or two previous values.
as we iterate that, aren't we using the values of
Actually,
x that are far
yi stays the same, so I'm just gonna keep iterating and changing and improving a little. So my second slope will keep changing, and hopefully it's gonna get more accurate. So I could just keep going on this one, right? And take this as an old value, compute the new value, and keep iterating until the two neighboring values of yi plus 1 are close enough. So then I'm hoping that I really improved my prediction. So that's so-called iterating on corrector equation.
So you still end up using Euler's method, you just do one more step to get a pattern.
Right, I just keep actually, and I can do a number of steps until the difference between the two estimates is small enough. So all of these values, so this is basically from now on, we started with Euler's method and it's a great visual method with the slope, but it's all about improving that slope. And we will list now actually this falls into so-called Runge-Kutta methods, and there is a lot of ways to improve that slope. Okay. So basically all of these methods, that's what they're trying to do. Now often you don't know what your function is, you don't know what you're solving for, so it's always hard, it's a little hard to gauge what precisely the correct, the best correction should be. Okay? So Heun's method, and we will actually get to the example, does improve on Euler's method. So this is an example how it could improve for the actual same step. I get much better. So this step H in both of these methods that I used is the same. Okay? So it might take me twice as smaller step for Euler's method to actually get this accurate. And Heun's method improves it. Okay? So this is actually, so this looks a little scary, but this is actually a general framework of all of these slope estimating methods. So my general form is yi plus 1 is yi plus phi of xi, yi, h. So this is some slope that depends on my current points, xi, yi, and my step size h. And this slope has the following form. It has a coefficient a1 times k1, where k1 is the value of f at xi, yi. Then it has coefficient a2 plus k2, where this is a value of f at slightly further point down the line in between the 2 points that I'm trying to estimate. So these are basically a number of points that I'm taking in between my xi, yi and xi plus 1, yi plus 1. And I'm going to take a number of slopes, okay? And I'm going to find a way to do a weighted average of those slopes. Okay, so this is a very fancy looking and a little abstract, but that's all it does. I'm taking a weighted average with my weights A1, A2, and so forth of AN between n different slopes, K1, K2 through Kn. My first slope is at my starting point, and all other slopes are at the points in between xi, yi, and xi, yi plus 1. Okay. These are just that, so those are typically given. Okay, so those are telling me where to take the slope. Okay. And we're going to have the example. So these are, by varying these P's and Q's and A's, you can actually get all kinds of different methods. And I'm going to actually show you a scary table. Here are some of them. Okay, so you can list them. But one most famous one is the one that is so-called fourth order accurate. By fourth order accurate means that between my estimate and my actual value of the function that I'm looking for, the difference is on the order of this h to the 4. So as h gets small, that gets much smaller than if I had accuracy of h to the square. Okay? If I'm thinking in terms of Taylor series, when we chopped off for Euler's method, when we chopped off the first part that is actually our method, we had O of h squared. Okay? And that O of h squared actually ultimately piles up to the error to the O of h. So I'm on the order of h, and here this one is on the order of h to the 4. Okay? So the higher the order, the faster I'm approaching my true solution. For larger h, I can actually get pretty accurate. So this Runge-Kutta method is one of the, again, most classically used ones. So my coefficients are 1/6, 2/6, 2/6, and 1/6. So this is a weighted average. All of these coefficients, they have to sum up to 1, right? So if I had a half and half, like I had in Heun's method, that would be one way, one type of Runge-Kutta method. So 1/6, 2/6, 2/6, and 1/6. And then how do I get, which slopes do I get? I have 4 slopes, K1, K2, K3, K4. My K1 is this first slope that is just the slope to the function at point xi, yi. Okay. My second slope is basically getting, I take this slope K1 by 1/2 h, okay? And that's the next point where I'm evaluating the slope, so that is my slope f of x. And then I actually take this point, this slope K2, and I try to improve and get the third slope. And that final slope just takes K3 all the way by h. Let's do that visually. So now I narrated it. Okay? So at this point, xi, yi, this is my slope K1. Okay, that's f of xi, yi. I take that slope only for 1/2 h. Everybody with me? So I'm here at this point. At this point, I evaluate the slope at the function, and that's my slope K2. Okay? Back to the formulas. So K1 is f of xi, yi. That's my first slope. That's just slope to the function at xi, yi. The next one, I basically take this point by 1/2 h, and I take it by slope K1. So I take this slope, and this is my sort of next prediction, if you will. And at that prediction, I find the slope. That's K2. Okay? Then I'm actually, so this is my improved slope, this K2. I take this slope K2, and also I take it by 1/2 h. I'm right here. And then I find the slope at that point. That's the slope. This is in red. That's my slope K3. Okay? So this slope K3 is actually a slope at this point right there. Okay? And that K3, I now basically take all the way to my prediction. Okay? So this is my prediction, last one. Okay? And then I don't take that as my final prediction. I actually average all these slopes to actually get, and this is where in this particular case, I'm sort of right on the money. Oops. Yes?
So since this process of like putting slopes on top
Adjusting
of
slopes, yeah.
kind of iterative, can we vectorize our whole increment function?
Mhm.
Is that possible?
Yeah, but each previous one depends on the previous one.
Okay.
So K2 depends on K1, K3, so you kind of have to keep, yeah, you can't, that'd be nice, but no. Yes?
Another thing, the H in the formulas for the K1, K2 on the last slide.
So H is my step size. So on this slide,
Yeah, why is it H comma Y? What does that mean? Is they multiply it or what is that?
H, comma, Y.
Is that a comma right there?
Where?
Between the H and the Y of that?
This is function evaluated at 2 points. One point is xi plus 1/2 h, and the second point. So maybe having a little bit of more space, right? So the f is function of 2 variables, right?
Okay.
Yeah, so
Could you explain where they're getting the coefficients for K1, K2, K3, K4? Why are some of them 1 and 2 and 2?
why are so many more?
The
That's
coefficients.
just the choice of the method. Now, it would, if I did all of the numerical analysis of the error and how it goes through, then it would be obvious. But that's 1 week for us to go through. So, but basically they're chosen to zero out error. Okay? So there's analysis that is done, which is essentially Taylor series, between the solution and the Taylor series of it. And in that analysis, I'm essentially trying to zero in the difference between the two. I'm trying to make them as close as possible. And I'm basically making all of anything next to h to the cube and h to the square and h, I'm making it 0. And in the process of making it 0, that gives me the choice of these. Does that roughly make sense? So when I'm analyzing the accuracy, I'm using Taylor series formula to actually do that. And in that process, if I want to make this O of h to the 4, then all of the other terms have to disappear. And to make them disappear, that's what works. Okay? Does that make sense? So somebody else did it. How's that? And it would be too lengthy for us to actually go through the proof of that accuracy. Right? All right. So that basically puts me right on the money. And this is what I'd like you to understand intuitively or geometrically, that these averaging all of these slopes really improves my slope, ultimate slope. Okay? So we will get to program this on Wednesday.
When we actually program it, how many different slopes should we average?
Huh? 4. In this case, 4. So this is 4th order.
But if we do it with a computer, do we do like 100 slopes average? Or do we do
No, 4 is, you don't go beyond 4th order rarely. Sometimes 5th order, but that's when you have very, very finicky methods that require super high accuracy. Most of the time you're happy with the 2nd or 3rd order.
Yours today.
Yeah, so this is programming next time.